Before physicists could accurately measure time using devices such as stopwatches, measuring the acceleration due to gravity from time and distance data was very difficult. So in the late 1700s, George Atwood devised a plan using a pulley system and two masses, which is now called the Atwood machine. Here is a simple diagram of the machine. We see here one mass, which is the larger mass, M1. This is experiencing a force due to gravity or a weight force of mg. The smaller mass, labelled here as M2, acts as a counterweight. It reduces the acceleration of the system. So here we see the weight force, or the force due to gravity, acting on mass 2 is m times g. We see the force vector here, the size is less. So this downwards pull, or the weight force on mass 2, is transferred by the string as an upwards force acting on mass 1. So therefore, the net force is less on mass 1. From Newton's second law of motion, we know that F net equals mass times acceleration. So the acceleration that the object, the mass, will experience is F net divided by m. However, here the mass is the mass of the entire system, so m1 plus m2. Now to add these two forces, we need to come up with a positive direction. So here we will define anti-clockwise as the positive direction. Okay, so here we can't use down because the pulley system makes the direction of the forces a little bit harder to distinguish. So when we do that, we see that the net force acting on the system is the weight force acting on mass 1 plus the weight force acting on mass 2, but here the weight force acting on mass 2 is in the opposite direction to our direction defined above. So then, the net force can be seen as m1 take m2 times the acceleration due to gravity. So here we've just factorised g out. So then the acceleration of the system, A, is equal to F net divided by m, as we saw above. So the acceleration is equal to the net force divided by the total mass of the system. So we're going to look at some data that I gathered to investigate the relationship between the acceleration of the masses and the mass difference. So in our experiment, the independent variable will be the mass difference, and the dependent variable will be the acceleration of the masses. Now, before we start collecting data, we need to write a hypothesis. So our hypothesis should state how the dependent variable, the acceleration of the masses, changes as we increase the mass difference. So as the mass difference increases, the acceleration of the masses will increase. However, there are lots of different ways this might increase. We need to give a little bit more detail here. Here we're expecting the increase to be at a constant rate. That means we're expecting a linear relationship between the mass difference and the acceleration. We should also support this hypothesis with some brief reasoning. So as the mass difference increases, the net force acting on the masses will increase. Thus, according to Newton's second law of motion, we're expecting the acceleration of the masses to be proportional to the net force. What this relationship means is that if we plot acceleration against net force, then we're expecting a linear relationship whose y-intercept is 0. Any experimental apparatus that we use will not be perfect. There will always be variables that we endeavour to control but are unable to do so perfectly. One example of this is in this setup when I let go of the masses Ideally, the masses would be stationary when I let them go. However, as you'll see in the videos, there is still some movement. It's really important that we understand this apparatus, even though we don't get to physically use it. Now, the mass data was collected using scales with a precision of 0.1 grams. The acceleration data had a precision of 0.1 centimeters per second per second. This acceleration data was obtained using a light sensor and this pulley up here connected to a smart timer. So what happens here is the light gate has a laser which can pass through and be sensed on the other side of our light gate, and when the pulley moves around, it blocks and then unblocks, then blocks, then unblocks the laser. And this pulley, the thickness of these black segments here is very well known. It's a very precise device. So what the smart timer can do is measure the amount of time it takes in each of these intervals to turn around. So then, as the pulley turns, it will spin faster and faster and faster. So the amount of time it takes for the laser to disappear, then reappear, so to say, on the sensor, will be getting smaller. And the smart timer uses that information to calculate an acceleration. So we see here the two masses. This is the counterweight, so this is the lighter mass. Here we have a 50 gram hanger, plus a 50 gram slotted mass, and an extra 7 washers. These are the masses that I'm going to transfer from one mass to the other mass. Here I have a 50 gram hanger and two 50 gram masses. So this is to ensure that this mass is heavier than the one on the left, the counterweight. Also here, we'll see, well, why did I make the decision to have this extra mass? Well then, the net force is coming from the difference of mass, which is obtained by moving the washers. The acceleration of the masses will be directly proportional to the net force and inversely proportional to the mass. What that means is, if I have a very low mass, I'm going to be obtaining a very high acceleration that my pulley and smart timer will struggle to measure. So I've added extra mass here to reduce the acceleration I'm going to record, to enable me and my device to record it accurately. Further points here, we see some string attaching the two masses. There's also a bit of extra string here which I've used, you'll see in the videos, to attach to this point here, just so I can record more easily. Ideally that wouldn't be there. The pulley is very good. If you spin it, it'll spin for a long time, indicating that there is not much friction present. The bearings inside the pulley are very good. I've clamped the tripod to the bench to try and limit movement. Also up here, I've tightly adjusted this fixed point to try and limit movement as well. But you might want to keep an eye on the video here. I'm not too sure how well I did here. When you have a lot of movement with the masses, the position of this pulley might change during the experiment. So now we're going to observe the different runs. I've labelled this run 0. That indicates that I've transferred no washers from the counterweight to the heavier weight for this run. The mass difference for this run was 11 grams, and we see that the smallest acceleration recorded was 17.8 centimeters per second, and the greatest 21.5. The mass difference for this run was 22.2 grams. The smallest acceleration recorded was 56.1 centimetres per second, and the greatest 62.6. The mass difference for this run was 33.2 grams. The smallest acceleration recorded was 91.2 centimetres per second, and the greatest 97.5. The mass difference for this run was 44.2 grams. The smallest acceleration recorded was 128.9 centimetres per second, and the greatest 132.0. The mass difference for this run was 55.2 grams. The smallest acceleration recorded was 159.6 centimetres per second, and the greatest 168.0. The mass difference for this run was 66.2 grams. The smallest acceleration recorded was 175.9 centimetres per second. The greatest was 204.7. The mass difference for this run was 77.2 grams. The smallest acceleration recorded was 226.8 centimetres per second, and the greatest 234.9. The mass difference for this run was 88.2 grams. The smallest acceleration recorded was 245.9 centimetres per second, and the greatest 267.8. Here we see a table summarising the data I gathered. The mass difference for each of the runs 0 through to 7, is recorded in grams, and we see the precision is to the nearest tenth of a gram. The acceleration for each of the trials and the average is recorded, with the precision shown to the nearest 0.1 centimetre per second. Also, we see a plot of this data. Here we have the average acceleration on the y-axis plotted against the mass difference in kilos. I've changed the units here to SI units to make the analysis of the gradient in the task much easier. So we see here the data values. I've used Excel to put in a trend line or a regression line through the data. This is the equation that Excel gave me for the trend line. So y equals 31.109x minus 0.0999. The r squared value is 0.9989. What this statistic means is that 99.89% of the variation in acceleration can be attributed to the variation in mass difference. That means if we want to make predictions of acceleration for the system, knowing the mass difference can predict that value very accurately.